In this installment, we're going to look at conservation of energy of free-falling objects. And I thought we'd start out, since our example is going to be dropping something from a tall building, I thought we'd just put the tall buildings in context. You can see here from this map, there are buildings located. We have Asian buildings, tallest buildings. We have Europe, tallest buildings. If you notice that the Asian tallest buildings are China, in the Middle East, and European all tallest buildings are in Russia. And the US, virtually all of them are in New York, with one in Chicago. They're scattered throughout South America. Most of the tallest buildings are in South Africa, with a couple in Kenya. And then we have all the tallest buildings in Oceania in Australia. So in that first category, Asian buildings, you can look, we've got the Burj Khalifa, which is at 822 meters, less than a kilometer tall. The tallest building we have constructed is less than a kilometer tall, but it is by far the tallest. The next one is almost 200 meters shorter. And notice that building is not even, it's not even counting any kind of radio antenna. Also the second tallest building, so that the Burj Khalifa in Dubai. And we got the Shanghai Tower in China. The next one's in Saudi Arabia, the Clock Tower. And then we've got China and China. So 3 of the 5 tallest buildings in Asia are all in China. And then we look at the tallest in North America is One World Trade. And when we look at the building itself, the deck, and we compare that across all of these, well, it's actually not even remotely close as tall as the others if you don't count the radio tower. And our new Central Park Tower that just completed is quite a bit taller, at least in terms of the building, minus the radio tower, than the World Trade Tower. And the only non-New York building is the Willis Tower, which was also called the Sears Tower. It used to be called the Sears Tower when that used to be a company. And when we look, here at the tallest building in Europe, the tallest building in Russia is 460 meters tall, which puts it on a par with this building here, Central Park Tower, and that point, if it's occupied, is taller than the observation deck of the World Trade Tower. So they'll just put those buildings in context. I find that kind of interesting. So let's look at our example, our scenario we're going to look at in great depth. We have our friend a pangolin who is at street level, and they take the elevator up street level, and they get all the way up to the observation deck, our friend the pangolin. So what we have that's occurred at that point is we have the work being done, and that work then goes into gravitational potential energy. The work, or the energy that came from that, was chemical. Chemical energy in our bodies, burning fuel, did the work to bring us to our gravitational potential energy. And of course, the pangolin who's now at the top of the observation deck, had recently acquired what is actually an official pangolin backpack designed to operate and be reminiscent of a pangolin. There's a number of different companies that make pangolin backpacks that has a 25 kilogram mass. And the pangolin, after having done all that work, is eventually going to drop it off the top of the tower. But I would like for you to consider, with a height of 541 meters, these lines marked across it, how far apart are they? What would you say would be the heights of those markers? If we're going to try to handle a value, we put 0 here, and we try 100, 200, 300, 400, and at an equidistant of about 500 would be here, and that would take us to about 540. So we would say those markers are 100 meters each. So I'll fill that up in my table here: 0, 100, 200, 300, and 400 meters. And that's where the pangolin is with their backpack. Now the potential energy has increased as the pangolin went up in the elevator. And that gravitational potential energy is mg delta z, I would like you to compute the gravitational potential energy of the backpack as it went up the elevator and to fill in the table for potential energy. The mass is 25, the acceleration caused by gravity is 10, and then we have our delta z. So in any case, it's going to remain the same as this 250, so that's times the height, the delta z. So it's 0, the potential energy is 0. So then 100 times 250, so there's 250 times 100, add 2 zeros. And 200 would be twice that amount, so that would be twice 250, or 500 plus 2 zeros. 3 times 250, 750, plus 2 zeros. And lastly, 250 times 4, or 1,000, and 2 zeros. $1,000 and 2 zeros. So that gives us 75,000, 50,000, 25,000, and 100,000. So we've done this work in our system. We've got gravitational potential energy. And when the pangolin drops it off the backpack, drops it off the top of the tower, that we know that from the law of conservation of energy now, the system consists of the backpack at that point in time. And so that gravitational potential energy is going to be converted into gravitational potential energy and kinetic energy. And then that gravitational energy, all of it will be converted to kinetic energy at the instant before it hits the ground. So next in our table, I'd like us to think about the total energy of the system. We know at the top that the backpack, before it's released, has 100,000 joules of potential energy, but it's stationary, so its kinetic energy is 0. And that means the total energy of the system is 100,000 joules at the top of the tower. So what I would like you to fill out for the rest of the table is what happens to the total energy as the backpack falls. We'd like to fill in that whole column for the total energy. Because energy is conserved, the energy of the system is the backpack, that total energy of the system is going to remain the same. So it is 100,000 all the way down. Now, when we put this at a 0 height, this sometimes gives a confusion that it's 0. Well, it's at a height of 0, the backpack isn't moving, it's already crashed. So when we define this 0 point, we're defining it as the instant before impact. Similarly, the potential energy of 0 is the instant before climbing. So it's not after the impact, it's the instant before the impact. So given that the total energy of the system is 100,000, and because of the law of conservation of energy, which says the initial energy equals the total energy of the system at every instant in time and the final energy of the system, I would like you to determine what the kinetic energy would be and fill in the table. Well, we can see if it must add up to 100,000, then the kinetic must be 25,000 there, and then 50,000. And then 75,000, and then 100,000. Since the potential energy is 0 and the total is 100,000, the other must be kinetic energy. And so what we can see then is that the potential plus the kinetic equals the total. And that shows us that the total energy of the system is conserved. The total mechanical energy of the system is also conserved. So if we were to write an expression for the kinetic energy then is equal to the total energy minus the gravitational potential. And that's exactly what we did. 100 minus 100 is 0. 100 minus 75 is 25. 100 minus 50 is 50. And so on. What I'd like us to consider next is the velocity. Now, at this moment in time, we know the kinetic energy is equal to 1/2 mv squared. So by that same token then, v squared equals 2ek over m, and therefore the velocity is the square root of 2ek over m. So I would like you to do the calculations to find the velocity and fill in the table all the way down. So let me start by filling this in at every juncture. So we've got twice 0 over 25. We have twice 25,000 over 25. We have twice 50,000 over 25. We have twice 75,000 over 25. And lastly, we have twice 100,000 over 25. Now, resolving these values, of course, this is 0. We knew the velocity was 0. There's 0 kinetic energy. But this 25 cancels. This 25s cancel out, and so we're left with the square root of 2,000. And by that same token, we're left for the next one, the square root of 4,000. And for the next one, the square root of 6,000. And lastly, that reduces to the square root of 8,000. And then dividing those out, we get 31.6 meters per second. And I'm using 3 significant digits because we were given a mass of 25.0. And then the next one works out to be 44.7 meters per second. So we can see we went from 0 to 31.6 meters per second. And then during the next equal change in energy, we went to 44.7, so an increase of 13. And then with the next exchange, we go to 54.8, so that's about 10. And then lastly, we end up with about 63.2, which is about 9 change. So we see the velocity increasing. Now, we could have solved this by kinematics, but using it by energy is actually quite a bit easier. So we know the impact velocity would be 63.9 meters per second. So now some of you may be wondering, what does happen to that kinetic energy? The law of conservation always holds. So where does that kinetic energy go? Well, that kinetic energy goes into what's called degraded energy. It's no longer available to do useful work. No longer available to do useful work. And where it goes then is it goes into thermal energy, it goes into vibrational energy, it goes into sound energy. And so it goes into these other forms that are degraded energy. So what we have is, beforehand, we have work done on the system. That work done on the system goes into gravitational potential energy. It converts back and forth between gravitational and kinetic until it's all kinetic. And that kinetic energy is then transferred outside the system into thermal, vibrational, sound energy. And so that is how we apply the law of conservation of energy to a free-falling object.